see.
So far, we're getting good questions, so keep them coming whenever you.
Okay, so this last one is using qubit sizing function to control the cell size using some sort of field that you define. And so the way that you do this, first you create a mesh using with uniform properties, and this is a real simple mesh, so I think I'm just going to look in ParaView. So you can look at Exodus files within ParaView. So what we've done, we first created just a real simple mesh that's just like this, and it has uniform resolution, so you can see that. But what we've done in a Python script right here is we've ingested this uniform resolution mesh, and then we've defined 2 extra fields that we then put back into the Exodus file. One is using a spatial database that this script reads, and the analog would be, for instance, if you're doing a dynamic problem, you typically want your cell size to be proportional to your shear wave speed. So that's the type of thing that this is meant to represent. The other example is where we do it as a function of the coordinates. And this would be the case, for instance, if you want your cell size to grade away from a particular feature in the mesh. And so that's what we've done with this one here. So once we've done that, you can look at, this is the database. So here we've defined a cell size based on values that we read from the database, and you can see that what we have here is a vertical variation in properties that we use to determine the cell size. The other one is an analytical function, and it looks like it's some sort of spherical function here. So it dies away with distance from the center. So once we put that into qubit, then we can make use of that to create a new mesh where the cell size is based on this function that you see. So here's qubit again. I'll set my directory. Okay. And then, oh, shoot. I hate it when it does this. I know what I'll do. Okay. So hopefully qubit shows up okay. Oh, we'll do it with the analytic function. So we've already created our uniform resolution mesh, but what we have to do the same geometry for our new mesh that we're creating. So we'll just do that real quick. There's our geometry, very simple. And then we're going to loop over. We have 3 volumes here corresponding to 3 blocks. And for each of those, we have to associate the cell size function. And once we do that, then it'll have the information that it needs to create the variable size mesh. So we're going to loop over that. That's another thing you can do in EPRA is doing loops. So it associates it for each block. So we've associated this cell sizing function. And then we're going to tell it the sizing function type is Exodus. We're going to give all the curves a scheme of stride. So let's see what happens if we do. Not much. Maybe that doesn't show up in there. Okay, then we're just going to start generating the mesh. We have our viscoelastic volume, which is this bottom part, and then we have the top parts, which are elastic positive and elastic negative. So we'll go ahead. Okay, so what you can see is that now, starting from a uniform resolution mesh, we gave that mesh a sizing function, which looked essentially like this. And then we created a new mesh using that sizing function. And so we get fine discretization right here close to the fault, and then it grades out as we move further away. And then there's really not much left to do. We can smooth it to improve the element quality. And that's essentially it, because the rest is the same as everything else. You have boundary conditions, and then you export the mesh. Actually, in this case, I guess we didn't bother with boundary conditions since we're not actually doing a problem. Okay, so we can actually look at that. I'll go ahead and do preview. Oops. Let's see, do we see pair view, or does it need to be over here? See it? Okay. So all right, so what we have, this is the end result, the mesh that we created, and this was the uniform resolution mesh that we used to define the sizing function. So that's pretty much it for the those examples. Do you have questions?
A couple comments to add is that you can't use this sizing function approach with a hex mesh. You can only do it with a tet mesh, and but you can also do it with triangular meshes. So triangular meshes and tet meshes, but not, you can't create your sizing.
Yes. Okay. What's up? Yeah. No, I think that's dependent on your computer. That if you have a lot of memory on your machine, then you should be able to handle a pretty large mesh.
The 32-bit version on the Mac and on obviously can't generate as big a meshes because they can't access all of the memory on a 64-bit computer. So even the Mac version is sort of somewhat limiting compared to the Linux version, because the Linux version you can get the 64-bit version, but there's no 64-bit Mac version available. So that does limit, so that you can't use all of your available RAM on the 32-bit version. But the 64-bit version, you can access all your RAM. If you're trying to generate a really big mesh, then the recommendation is to get everything set up using the GUI, but then you can run in batch mode without the GUI, and without using the GUI or graphics, it'll use even less memory when you generate the mesh. So you can really try and maximize the mesh size. But we've generated several million size meshes, and Pilot also has the capability of then further refining the mesh once you get it into Pilot. So you can increase or decrease the mesh size by a factor of 2 within Pilot, and it'll do that in parallel. So that allows you to generate, sort of on the order of about Any other questions?
Let's see how to set the BC. Well, do we have one that's coming up for that?
Do you mean actually creating the node sets, or do you mean defining like the type of boundary condition and sort of values for boundary conditions? So defining the node set for the boundary condition is really no different than what we had in our very first example in the last session and what Charles went over in the previous session. Basically, you select, if you're doing 2D, you select curves. In 3D, you select surfaces, create groups, and then once you have the group with the nodes you want, you create a node set from that group. And that's really it. It really doesn't depend on how complicated.
Okay. Trying to think what else. Again, we went through one, well, your quick example, because what I've just gone through here is purely meshing. It's not how to go from meshing to running pilot. But yeah, I don't. We weren't real. Were we going to cover that? Well, not really, right?
Well, we cover sort of setting up the boundary conditions as we're doing the other problems. So like for the Green's function is in the next session, it'll be pretty straightforward. But the fault friction will be moving the boundaries, deforming them. And then if there's specific questions about types of boundary conditions, we can go over those in any of the examples now, or so if people want to know how to do a time-dependent traction boundary condition or a time-dependent displacement boundary condition. They also discussed very extensive.
Yes, an exercise for the reader. The mesh for this sizing function example is very similar to the ones for the 3D hex 8 examples. If you get motivated, it might actually be interesting to take this mesh and then run one of those examples. I mean, you would have to change it a little bit because the 3D hex 8 mesh, the fault goes all the way through. But that would be an easy thing to change. Ah, you can use, well, do you want geographic coordinates or a geoprojected coordinates? Yes. Should we turn this mic on? Um,
So one option is you can actually you can do your mesh in a geographic projection. Pilot actually has coordinate systems for so you could, if you like, were bringing in your geometry into Qubit, bring it in, project it into the geographic projection, do everything within Qubit in the geographic projection, export it. Your spatial database can be in a different geographic projection, and Pilot will take that into account when it does the interpolation. So you can work in a geographic projection if you'd like, or you can put everything, in sort of some sort of other Cartesian coordinate and then reproject it back to a different projection. I generally prefer to pick a geographic projection that's going to have sort of not much distortion for the particular domain I'm working in, and I pretty much stick with that from the meshing all the way through to the visual. Sometimes in the visualization I'll switch to a different projection. And there's a example, there's a two-cell TET4 example. It's discussed in chapter near the beginning.
let's see, how the meshing size can affect the results in the case of problems for inversion of geodetic data. Well, I think, yeah, you want to, because the thing is, you're representing the displacement field, you know, as like piecewise linear functions. So it's, I think to do that, what you actually have to look at is exploring a few different options for meshing size and see how much your solution changes at the points where you have observations. So a simple way to do that is just using Pilot's uniform refinement, and you can see how much the solution changes for, like, say, a particular slit distribution on a fault. You can try it at one resolution, then try it again with uniform refinement and see how much it changes.
Charles, do you want to comment on, like,
Well,
how
yeah,
fine
because
you want to?
yeah, there's two issues. One is representing the, say, surface displacements, and the other part is how finely you want to represent the slip on the fault. And yeah, that, I don't know, that's a kind of tricky question, because one thing that people always try and do is duplicate Okada results using the finite element results, but that's, I don't know how productive that is. It just means that you're trying to use a different type of fault representation and to show how well you can approximate a different method. I think it, for instance, if you have INSAR that you're inverting, then you can obviously, you can resolve co-seismic slip much better than if you just have a few scattered GPS stations. I don't have any kind of hard and fast rule for, like, what you can, what scale of fault slip you could resolve with a, or a given data density. I don't know. Does that help at all? The answer is I don't have any kind of numbers. I think you would need to do, you would have to do a resolution test is what you'd need to do. I would think if there's a simple,
So we can play around with that a little bit
I could do
in
that.
the greens function example tomorrow. But in session. Although we don't have that many points. Yeah, we don't have that many observations, but you can sort of, we could make it really coarse. And
like in the 2D example. Yeah. Yeah.
Yeah.
Let's see, with greens, if we do refine uniform, then it'll generate one for every, for all of the new vertices, right? That might be an interesting thing to try.
Yeah. So the example we're talking about is in 2D greens functions. There's both a strike slip and reverse example. They generate a forward problem with synthetic data. It's sort of our fake observed data. Then we compute the greens functions for a number of points on the fault, and then set up a very simple inversion with different smoothing parameters. So it's pretty easy in that case to simply, you could just, it's a 2D example, so it doesn't take very long at all to generate the mesh. So you can sort of do the forward problem at a reasonably high resolution and then regenerate your mesh and iterate on a coarse resolution and compare the results.
I have to remember how where refinement fits in. We don't have an example with it, do we?
Yes, we have 3D Tech for step 02 and step 04. It's just one line.
There we go.
I think it's mesh generator refiner in the setting.
Right, just for fun. Yeah, that might that might be a good thing to try tomorrow.
Any other questions? Okay, well, I think we can wrap things up if there's no further questions. We suggest, if you have time tomorrow and later today to work through other examples and sort of try some of the things out that we've covered, you can go back and we'll have a streaming version of this session online. So if you want to go back and go through the example and follow along, and then replicate the steps that Charles did in this example or what I did in the first session, those will be available. You can also go through the manual and sort of find say a particular problem that looks similar to what you want to do and see how far you can get, and then come back with that may generate some additional questions that you have that we can answer in a future session. And we'll post, there's a link to the Q&A log on the agenda webpage near the top. And I'll add the question and answers from this sessions to that in the next 5 or 10 minutes and get that uploaded.
Okay.
So thanks for participating. You lucked out with the smaller of the two sessions. We expect a pretty big session tomorrow. And we'll also be updating the Q&A from those sessions. So you may, want to check out and sort of see what shows up in the Q&A log tomorrow to see if there's a similar question to what you have. There may be an answer to one of your questions there. But thanks for just participating, and we'll see you in a couple days. And if you have questions between now and Wednesday, you can always email